After last week's lecture, you should have a solid grasp on regression with one independent variable and one dependent variable, also called a bivariate regression. But it's possible, maybe even likely, that the coefficient in a simple bivariate regression is a poor estimate of the causal relationship between two variables. For an example, let's think about the question of whether going to an expensive private college raises your earnings.
Yes, you heard me. An English major. I paid $120,000. How dare you clap? How dare you clap for the worst financial decision I ever made in my life? I paid $120,000 for someone to tell me to go read Jane Austen, and then I didn't.
Let's say we have two variables, one indicating whether or not an individual attended a private college, and another one indicating a person's earnings. If we run a simple linear regression with the natural log of earnings as the dependent variable and private schooling as the independent variable, then we get an estimated coefficient of 0.135 with a standard error of 0.055, resulting in a huge t-statistic of 25. People who attend private schools definitely earn more money than people who attend public schools. But does attending private school cause a person to earn more? To answer this question, let's think about omitted variables. Do people who attend private school and people who attend public school have any differences on average besides their education? Well, yes. Students who attend elite private schools have better high school grades, higher test scores, and are more motivated, among other things. In order to know the true causal effect of private schooling on earnings, we must compare privately and publicly educated students who are otherwise identical, also called a ceteris paribus comparison. How can we do this? Let's take a look at some example data. Looking at this scatter plot, it's pretty clear that our x and our y variables are positively associated. Running a simple linear regression confirms this. The estimated slope coefficient for the data in the scatter plot is positive and statistically significant. However, let's say you learn that this data consists of 5 different groups of observations. We suspect that people's choice of group might be an omitted variable that affects both x and y. How can we account for this possibility? Well, a basic way to do this is through what's called conditioning. We can condition on our group variable by estimating the slope coefficient for only those individuals in group 1, then estimating the slope coefficient for only those individuals in group 2, and so on until we run a regression for each group. Then, we look at the average value of the slope coefficient across groups. In this example, each group has a regression line with a slope close to 0, indicating that there's no relationship between x and y once we condition on the group. This is an example of how much our results can change once we account for omitted variables. Conditioning on our group variable took us from a strong positive relationship between x and y to basically no relationship. How could we use conditioning to account for omitted variable bias when it comes to private schooling? Economists Stacy Dale and Alan Kruger had an idea. Create groups of students who applied and were admitted to the same schools, but attended different schools, and then calculate the effect of private schooling on earnings after conditioning on membership of these groups. So, for example, all of the students in one group might have applied and been admitted to both Harvard and UVA, but some of the students in the group attended Harvard, maybe since it's more prestigious, and some attended UVA, maybe because it's cheaper or closer to home. Since all the students in this group had the grades, test scores, and motivation to be admitted to both schools, comparing the students in the group who chose Harvard to the students in the group who chose UVA should give us a much more accurate estimate of the effect of going to a private college on your earnings. Dale and Kruger constructed 150 groups of students who were admitted to different combination of schools, and then estimated the effect of private schooling within each of these groups, conditioning on the group variable. When they condition on the group variable like this, the authors find that the estimated effect of private schooling on log earnings falls from 0.135 to 0.007, with a standard error of 0.038. That results in a t-statistic of 0.1842, so the wage premium associated with private schooling is no longer statistically significant from 0. In plain language, once we account for selection bias by conditioning, there's no longer any evidence that private colleges boost your earnings any more than public ones do. This is great news for those of us attending large public universities. Okay, so conditioning is one way that we can control for the presence of confounding variables. But it has some limitations. Most obviously, it only really works with confounding variables that are discrete rather than continuous. If we were to try to condition on a continuous variable like height, for example, then we would only be comparing people who are 5 foot 5 inches and 3/8 inches to other people with that exact same height. There would be so many groups with so few people in each group that we couldn't identify the relationship within a group with any degree of confidence. However, there is a way for us to make ceteris paribus comparisons even when we have confounders that are continuous: multiple regression. Let's take a look at a slightly different research question. Rather than looking at the payoff of private school versus public school, let's examine the return to education more broadly. If we just make raw comparisons using this example dataset, we'll find that each year of education is associated with an increase in yearly salary of about $7,000, and the relationship is statistically significant. Should we interpret this as the causal effect of education on earnings? By now, hopefully, you've spotted a potential confounding variable: ability. People who attend college are more intelligent on average, which also makes someone a better worker. In our data set here, we have data on each person's SAT score, which is a good enough proxy for ability. We can't condition on SAT scores, though, since it's a continuous variable. What can we do then? Well, let's take a look at a scatter plot of SAT scores, years of education, and wages in 3 dimensions. In 2 dimensions, our goal was to find the equation for a one-dimensional line that best fit the data. When we move into 3 dimensions, we can try to find the equation for a 2-dimensional plane that best fits the data, like this one. Notice that the edges of this plane are regression lines. We can interpret the slope of this edge as being the effect of education on earnings after controlling for ability, and this edge as being the effect of SAT score on earnings after controlling for years of education. If we go back into 2 dimensions, we can see how important it can be to control for omitted variables. This line is the relationship between education and earnings with no controls, and this line is the edge of our regression plane. It's the return to education after we control for SAT scores. If we don't control for the omitted variable, we're overestimating the effect of education on earnings. If our equation for our line of best fit can be written as yi equals beta naught plus beta 1 times xi plus the error term, then we can write the equation for the plane of best fit like this: yi equals beta 0 plus beta 1 times xi plus beta 2 times zi plus the error term. Just like last time, our goal is to find the values of beta 0, beta 1, and beta 2 that minimize the sum of squared residuals, which we can write an expression for like this. Okay, so now we just need to solve this optimization problem like we did last time. But as a gift for, Asiatic Fleet Memorial Day, we'll be skipping over the proof. That means you won't need to know it for any assessments, but it can be found in this week's lecture slides if you're interested, or I'm happy to work through it in this week's Q&A video if you'd like. If we solve this system, relying on our zero conditional mean assumption, we end up with this expression for beta hat 1, where this term, r1 hat I, is the residual term from this regression, where we regress xi on zi. Recalling that the mean of the residuals is 0, we can rewrite this expression to look like this, which should look familiar. It looks exactly like our expression for beta hat 1 in a bivariate regression, but instead of the actual values of x, we use the residuals from the regression of x on our other independent variable. Why does this matter? Going back to our education example, we'd calculate the effect of education on earnings after controlling for SAT score by first running this regression, then regressing earnings on these residuals like this. We could also run this regression and use these residuals to find the effect of SAT score on earnings after controlling for differences in education. This works because this residual can be thought of as the portion of education that is uncorrelated with SAT score. So this coefficient becomes the earnings effect of a 1-year increase in education after controlling for SAT score. This is called the partialing out interpretation of multiple regression. What exactly happens to our estimates when we omit an important variable from our analysis? Let's say we don't include SAT score in our return to education regression, and instead just regress wages on years of education. We would use this expression to find the slope. If we substitute in our expression for earnings in terms of education and ability from earlier, we get this. If we rearrange, simplify, and take expectations, we're left with this. We can make one more substitution. Looking at this fraction and recalling this regression where we got our residuals, we can see that this fraction is the slope term from when we regress education on ability, leaving us with this expression for the slope when ability is omitted. What is this telling us? Well, let's sign these two terms. Beta 2 is the effect of SAT score, or ability, on earnings. Do you think it's positive or negative? It's almost certainly positive. Smarter people are more productive, leading to higher pay. What about this term here? It's the relationship between ability and education. Its sign will also be positive. Higher ability people are able to obtain higher levels of education. Thus, this formula is telling us that the expected slope when not controlling for ability will be an overestimate of the true effect of education on earnings. This formula quantifies the level of omitted variable bias present. If this term is 0, then leaving out a variable from our regression won't change anything. We can see that this term will equal 0 if beta 2 equals 0, meaning that our omitted variable isn't correlated with our dependent variable y, or if this term, gamma hat 1, equals 0, meaning that our omitted variable isn't correlated with our other independent variable x. Just like with bivariate regression, we can also show that the sample multiple regression slope is an unbiased estimator of the population multiple regression slope under the zero conditional mean assumption. The total, residual, and explained sum of squares also carry over from bivariate regression, and we can calculate the coefficient of determination, or r squared, in the same way. For multiple regression, we interpret the r squared as the proportion of variation in our dependent variable that is explained by variation in all our independent variables. Finally, we can find the variance of each of our slope coefficients using this formula, where this term is the r squared from our side regression between our independent variables here. However, this measure of variance still depends on our homoscedasticity assumption from last week, where we assume that the variance of the error term is uncorrelated with any of our independent variables. What makes multiple regression so useful is that we can expand it to work with any number of independent variables. For example, we could have 3 independent variables like this, x1, x2, and x3. At this point, we can't really visualize what we're doing by fitting a 3D object to a 4D scatter plot, but the math to minimize the sum of squared residuals works the same. There's just more of it. To find beta 1 here, we'd need to estimate this model on the side, for which we'd need to estimate these two models, and that's just for 3 independent variables. Some models can have dozens or even hundreds, so multiple regression at this scale pretty much requires the use of statistical software. So, let's review. Multiple regression allows us to make ceteris paribus comparisons by controlling for potentially confounding variables. If we fail to control for a variable that is correlated with an independent variable and correlated with our dependent variable, then we have omitted variable bias and are either over or underestimating the true effect of our independent variable on our outcome. We can conduct statistical inference on each of our slope coefficients using this variance formula. And we can calculate the r squared for the entire regression using the total, explained, and residual sum of squares. We'll look into ways that we can expand multiple regression to be even more useful. It can estimate nonlinear relationships between variables, it can incorporate qualitative information, and we can find ways to estimate the variance of our slope parameters even in the presence of heteroscedasticity. However, even with all of these bells and whistles, it's important to remember that we can't always just add control variables to our regression model to find causal effects. We could have an omitted variable that's unobservable, either because it's not in our dataset, or it's difficult or even impossible to quantify, like personality or motivation. We could also have simultaneity bias, a case where x causally affects y, while at the same time y causally affects x. Econometricians have developed techniques that can address these concerns, and they typically use multiple linear regression as a framework to build around. That's a brief preview of what's coming up after the midterm.